Good evening, everyone. Our presentation is on a survey on robot localization in extraterrestrial environments. And here is a brief outline. We begin by discussing what is localization, why we need it, and where, as in which context we need it, and some of the feasible technologies in our context. These are dead reckoning, camera, LiDAR, wireless sensor networks, and then we compare and contrast these to conclude. So the most important thing is to discuss the context of the localization area. In our case, it's in an autonomous robot that works in an extraterrestrial environment. For example, Martian surface. So what exactly is localization? When you have a robotics system, you need to get the position and orientation of the robot. You do this by sensory inputs to the robotic system. You accumulate this over time and then extract the information to get the position and the orientation. So why exactly do we need this in extraterrestrial environments? This is because if we have a control station out here on Earth, the delay because of interplanetary radio communication would not enable real-time control of the robotic system, and hence you need autonomy. And the most important thing in autonomous navigation is localization. So we need to understand that the localization approach has to be very different from what we do here on Earth because of the absence of artificial landmarks. By artificial landmarks, I mean things such as streets, buildings, water bodies, and also because of absence of positioning systems. So some of the promising methodologies that we are going to look into are dead reckoning, vision-based algorithms, LiDAR, and wireless sensor networks. Usually we don't rely upon any single of these methodologies, and usually combine multiple of these to get a precise estimation. So the simplest of these is dead reckoning. Suppose we begin by knowing the initial position and orientation of the robot, and we we measure the speed and we know the direction in which the robot is traveling. It's pretty easy to get the current position and orientation. This is usually done with techniques such as wheel odometry or IMU, and the most popular techniques in wheel odometry are using of rotary encoders such as optical encoders, or you might even have heard of Hall effect sensors. But then again, these have errors per rotation which are negligible, but over a distance these get accumulated and become more significant. So for more precise estimation, we usually combine dead reckoning with other reliable techniques to get a more precise localization. One example is in the current Mars exploration rovers Spirit and Opportunity. They use onboard IMU sensors and wheel odometers to estimate the initial position and orientation. But in addition to this, to make the data more precise, they also have sun filters to point the pan cam that they have on board to point towards the sun, so that you get a more precise orientation. And you can actually see in the image, it's the pan cam used in Opportunity, and it has 2 degrees of freedom. It can pan horizontally and tilt vertically. So the combined information gives more accurate estimation for the orientation. Gautam is going to continue with this.
Hello. Camera has been a very major contributor for the localization of any autonomous body. So why not the robots? So generally camera is used in conjunction with several technologies like odometry, LiDAR, etc. So in our paper, we have discussed these methodologies using camera. So let us look at them one by one. First, the visual odometry. So what happens is, first you have to know the initial position of the robot, and we have to have a two camera thing, like so the left camera would take a picture and the right camera would take a picture, like since they are like both placed at a slightly different position, you get slightly different pictures of the scene in front of you. So using these pictures, you extract features, like features as in like the corners, like the top of some objects in front of you, like say rocks or something. So you get these, you extract these features, and then using something which is called as a stereo matching, you have to calculate the 3D position of these features with respect to robot in front of you. So you get at position P1 you get the 3D positions of the features in front of you, and then you move at distance d, and at the second position P2 you again repeat the same thing, and you get 3D positions of the same features in front of you. So using this slight difference in the movement of the features, like when you move forward, you get the actual distance the robot has moved, like using all the correlation. You have to correlate all the features that has moved through a distance, and using something which is called as least mean square or weighted least mean square methods, you can extract the distance the robot has actually moved. So next one is by remote viewing of colored cylinder. This is actually an interesting one. You have to have a colored cylinder, like if you see in the image, you have a color in each of the quadrant of the cylinder. Like so we know that when we move away from the object, we see the object like slightly smaller. So this fact can be exploited, and using this small formula, you see the distance of the camera from the cylinder can be known, and also the orientation. The orientation can be known by calculating the various amounts of colors you see. Like if you tilt a little towards right, you don't see green, then you see only blue and yellow. So based on that thing, you calculate like at what theta you are with respect to the cylinder. So next thing is using a 3D model of the rover. If you see, we have a 3D CAD model of the robot, and also an image is taken in the environment, and you have to correlate the 3D model with the image you have taken, and so that you'll get this, the position, the size of the robot, the size of the robot in the image will give the distance from the robot, and when you correlate, you get at what angle the robot is in front of you. The next technique is using celestial bodies. So if we take a star and join it to the center of the planet or any extraterrestrial body, you get a point where it intersects with the surface. That is called as the ground point. And at what altitude you see the star in the sky, that is called an altitude angle. So if you draw a circle, if you see in the figure, that's called an equal altitude circle. And if you see several such stars and you draw several circles, and the point of intersection of all these circles would give you the approximate position of the robot on the planet. So next thing is using satellite images, where you have to have the satellite images already taken. Then the camera on the robot takes the panoramic images of the environment, and then the features from the satellite image and the robot image are correlated, and then you get approximate position of the robot on the planet surface. So next thing is using LiDAR. This is same as using a camera, where just instead of robot taking camera panoramic images, robot would now take LiDAR scans of the environment, and the features are extracted, and correlation is done to get the localization of the robot. So this will be continued by Sanjay.
So I'll be talking about wireless sensor networks. Wireless technology is actually a very reliable technology for localization. It has been mostly used in indoor localization systems, and the most common is radio frequency, and Bluetooth, Zigbee, Wi-Fi, etc. come under radio frequency. And in a wireless sensor networks, as you can see in the picture, there are several reference nodes, and you have a blind node, which is your robot, and you calculate your location of the robot according to the reference nodes. So in order to localize your robot within the network, you have to know the position of your reference nodes predetermined. So that's the reason why wireless sensor networks has not been used very much in extraterrestrial environments. So it's very hard to deploy wireless nodes in an unknown environment. So you can use methods like lateration, angulation, and also you can combine wireless sensor networks with dead reckoning in order to get more precise estimates of your robot. So the first technique we'll see is wireless sensor network and odometry. In this technique, we use Zigbee modules based on the IEEE 802.15.4 for localization. So in this technique, we use both the wireless sensor network and dead reckoning techniques. And in wireless sensor network, you'll have a certain amount of error, which is almost constant throughout the robot's exploration. And for the dead reckoning, the error keeps accumulated, and it keeps getting bigger. And you can use a Kalman filter in order to combine both the sensor readings and get more precise value for localization. So, and the signal strength in this wireless network is more susceptible to attenuation due to like changes in the environment. So this can be overcome by using the next technique, which is low frequency and very low frequency electromagnetic signals. And in a low frequency, which is in the range of 30 kilohertz to 300 kilohertz, and very low frequency is 3 kilohertz to 30 kilohertz. So when using low frequency signals, you can almost have no error due to any obstacles or any unknown environment. So it is very suitable for extraterrestrial environments. And in this technique, we can use the angle of arrival measurement, which is by using the triangulation in order to get the location of your robot. So the accuracy of this technique mainly depends on the position of your nodes, and you can deploy your nodes in the environment in two ways. One is before deploying your robot, you can set all your nodes before deploying the robot, or after your robot has been deployed in the environment, you can shoot the nodes at a certain angle. In that way, you can know the location of your nodes and get more accurate localization. So the next technique is using the RFID, the radio frequency identification technology. In this technique, you'll have various RFID tags in your environment, and each tag has a definite range in which your robot can be, and you can actually get localization values using 3 phases. The coordination phase. In the coordination phase, what you do is your robot actually starts sending signal. I mean, it initiates the process by synchronizing with all your nodes. And next is the measurement phase, where you get the measurement of the distances by sending the signal. And the next is position estimation, where you calculate your position from the distances to the nodes. So you can obtain the precise localization using methods like Monte Carlo localization. So next is using radio signal mapping. In radio signal mapping, you use radio signal strength, and and you create a map of the environment, and you use Gaussian processes to build an online model, and according to the signal strength, you estimate the location of your robot. So the received power can be depending on these factors: the distance from the source, shadowing due to obstacles, and multipath phenomena. And finally, it is very hard to get precise localization in an unknown environment. So choosing a technique for localization actually depends on the application of your robot. So for long distance traveling robots like exploration rovers, global level techniques like LiDAR and satellite altimetry, along with local level techniques such as visual odometry, would be more reliable. And for short distance traveling robots like a mining robot, the local level techniques like remote viewing of color cylinder using camera or wireless sensor networks with dead reckoning are more suitable than global techniques. So these are the references.